The same thing is true here. If the size of the particle is right compared to the wavelength that you are shining, and if certain other conditions are right, you can actually have a resonance. And these electrons can start oscillating at very high amplitude. Actually, that is the reason why you have surface enhanced Raman scattering again. And this resonance is called surface plasmon resonance. Now, this word plasma refers to free charges, right? So you have these free charges oscillating on a metal surface, and you can have a resonance with respect to the input energy, and you can have what is called surface plasmon resonance. So in that sense, metals are obviously different from semiconductors.
You can have what's called surface, right?
Yeah, let's read this. I think that will be much better. So under some conditions, one can resonantly excite a surface plasma wave. What that means is electrons start oscillating. Okay? And at the interface of metal and dielectric. And this surface and this resonance is called surface plasmon resonance. So all that means is that you have a very efficient transfer of energy from the input light into the energy of electrons. Okay? And so of course, the question is, what do we do with this? There are obviously many applications, and surface enhanced Raman scattering is one application. But there's another very nice application that people are working on. So people are trying to make what is called light on a wire. Okay, and let me just spend a few minutes here. Obviously, we want to transmit as much data, as possible. We want to have very high bandwidths. Okay. And so one way of doing it, of course, is with the help of light and optical fibers. Light has a very high frequency, 10 to the 14 hertz. That's the reason why you can transmit large amount of data through optical fibers. I mean, these days, even your televisions or internet connections, everything, they are changing over from electric wires to optical fibers. And the reason why they can do it is because of this bandwidth. You have very high bandwidth. Frequency is very large. But of course, optical fibers tend to be bulky. Okay? You might say optical fibers have a diameter of say 100 microns, but even 100 microns are bulky. Okay? And you can make electric wires, metal wires, which are much thinner than that. I mean, you can have electric circuitry on a chip, and the width of an electric wire can be as small as few tenths of nanometers. So you can make much thinner wires, electric wires, as compared to optical fibers. But optical fibers have a high bandwidth, they can carry more data. Whereas in wires, what is the highest frequency that you can send? It's probably about 10 to the 9 hertz, microwave. Okay? You cannot send anything more than a microwave. Okay? So you have two different things. On one side, you have very tiny wires, but bandwidth is limited. On the other hand, you have these bulky optical fibers, but they have a very high bandwidth. And so the question is, can you somehow combine the advantages of both? Okay? So you want to have wires, but which can carry frequency of light. Okay? And that is what they are talking about here, light on a wire. Okay? And so maybe you can read some of this. Photonic components such as fiber optic cables can carry a lot of data, but they are bulky compared to electronic circuits. Electronic components such as wires and transistors can carry less data, but they can be incredibly small. So we want to have a single technology that has the capacity of photonics and smallness of electronics. That would be the best way to go. And so there are lots of research groups these days which are actually working on this. And of course, you can do it because I just said you can have surface plasmon resonance. You can, if you have the right conditions, you can make the electrons oscillate at the frequency of light. Okay? And of course, this oscillation can propagate along the wire. Okay? Of course, there's a lot of hype in this one also because it so turns out that these high frequencies are very lossy. Okay? So they can only propagate these very high frequencies over very small distances. But of course, you might say that really that is all you need. In very small circuits, you want to propagate only over small distances. So it has some promise and people are working on it. Okay, so I'll skip this. And again, this is something that probably Parmija mentioned yesterday. You can have, just like semiconducting particles glow with different colors, so you can have metal particles of all shapes, and you have a we have a colloidal solution of these metal particles. In this case, actually, it's a different type of a metal particle. You have nanoshells. So you have these silica nanoparticles covered with nanoshell. And if you just change the thickness of the shell, you can make it glow with different colors. And the question is again, why do you want to do that? And I just want to show one application or two applications. So this is some application of plasmonics. And okay, so you have this surface plasmon resonance. What that means is that one particular wavelength is absorbed very, very strongly. So it's almost like a filter. You can remove that wavelength out. Suppose I have a layer of these nanoparticles of some size, and if I'm shining light onto that, one wavelength will be absorbed very strongly, and that wavelength will be missing in the light that comes down. Okay? So people have actually used this as a filter. You know, some people have actually used this as a coating on top of some semiconducting devices, so that those you can remove the ultraviolet light out and it will not damage your circuit. In fact, this is again the reason why these days people are investigating coating solar cells with nanoparticles, because you can make you can increase the absorption in solar cells, because you can have this surface plasmon resonance at certain wavelengths. And this is a very nice application that I will talk about. It's probably the last application we want to talk about. So these nanoparticles, metal nanoparticles, have been used for what is called whole blood immunoassay. What that means is that suppose you want to find out what protein or what antigen is there in your blood. Okay? I mean, these days if you go to a doctor, I mean, if you are a male and beyond a certain age, they will test you for prostate cancer. Okay? And so they actually look for a certain type of protein in your blood, which is called PSA. And those of us who have gone to the doctor know that. So PSA stands for prostate specific antigen. Okay? And with many of the cancers, you have this very high growth of certain type of proteins, okay, which are associated with specific cancers. And so let's say I'm trying to detect the presence of certain protein in your blood. Okay? The one way of doing it is, let's say I have these nanoparticles. This is the antigen that I want to detect, these blue particles. Okay? And now you probably know, at least biology students know, that there's a very specific binding between antibody and antigen. Okay? Just like, if you have been bitten by a snake, let's say a cobra, then of course, for that venom, you have a very specific anti-venom, right? Venom is a protein, anti-venom is a protein, okay? So this anti-venom will bind to a venom and get remove it, okay? So there's a very specific binding, like a lock and key, between antibody and antigen. So let's say I'm trying to detect, this particular protein. So what I will do is, I have these metal nanoparticles, and on the surface of that, I will have the corresponding antibody. Okay. So if let's say I have a blood sample, and I mix it with these nanoparticles with the antibody, then of course you can see that you will form this type of a structure, because antibodies are binding to the antigens. And so now you can see that the optical property of this has changed, because the size has changed. And so here you had surface plasmon resonance for one wavelength. Here you have surface plasmon resonance for another wavelength. So the color will change. So it's a very nice, simple technique for, and it's a very specific technique, because you can, whatever antigen you want to detect, you can put the corresponding antibody on the nanoparticle. Maybe one more application. This, of course, I've talked about surface enhanced thermal scattering. There's a lot of material here that I will skip. And you can actually make different kinds of optical fibers, which are called photonic crystal optical fibers. Traditional optical fibers have a high refractive index core and low refractive index cladding, and the light is confined to the core. This is a different kind of an optical fiber, and it's a nanophotonic, photonic crystal optical fiber. And you can see here that it has a this is a 2D photonic crystal, a special kind of 2D photonic crystal, because it has a periodicity in 2 dimensions. Okay? So this optical fiber is very long, it could be hundreds of meters long, but it has periodicity in x and y directions. And now we have learned in one of the earlier slides that anytime you have a photonic crystal, there's a range of frequencies which are not allowed. There's a band gap. Okay? So suppose I'm putting that light in this optical fiber. Okay? It will be thrown out of this optical fiber because it is not allowed. So where does it go? It goes into the core. Okay? So this is a different kind of optical fiber which works by diffraction, not by refraction. And it has some advantages. And of course, if you have worked with an optical fiber, you probably know that optical fibers are good only for certain wavelengths. Let's say they're good for 1 micron light, 1.5 micron light. But let's say I want to put 10 micron light. Then it is not good because glass is very absorbing. Like 10 micron light cannot propagate through glass. But here I can have a hollow core. I can have a special kind of photonic crystal optical fiber. In the center, it's a hole. Okay? And now you can see that if I put this 10 micron light in this optical fiber, and if it falls within the band gap, it will be thrown off. But this light is traveling in vacuum. Okay, or air, and of course there is no attenuation in air or vacuum, for 10 micron light. So you can use this fiber for propagating those wavelengths which cannot ordinarily be propagated in ordinary optical fiber. So there are lots of applications, and maybe I think there are applications in bioimaging. Once again, here we have a rat, which has a tumor. And of course, all tumors are associated with certain kinds of antigens. And so I have these, again, nanoparticles with antibodies sticking to it. And these things can go and stick exactly to the tumor site. Okay? And so you can actually do the imaging because these could be quantum dots. You can shine light, they will glow with a certain color. Or you can have radioactive particles, they will again go and stick to the tumor. And you can do this gamma ray scintigraphy nuclear techniques. Okay, this is the final thing I want to show. This is something called targeted therapy with nanocapsules. Again, this is a very promising technique in nanomedicine that people are working. And I heard from some people that they are beginning to use in hospitals. And so what this thing is, again, let's say you want to deliver some drug to the site of a tumor. And once again, you have nanocapsules with the drug inside, and the tumor has antigens, certain kind of antigens. So you want to stick antibodies which are specific to that antigen. And this will go and stick exactly to the disease site. Okay? And so you have very little damage away from on a normal tissue. Okay? Normally, of course, if you have these chemotherapy or radiation therapy, there's a lot of damage in the tissue, other than the tumorous site. Okay? But with this technique, it's almost like a magic bullet. Okay, because it's like let's say I want to shoot some enemy. Okay, I can fire my gun at random, but the bullet will go and only go to the enemy and stick there. Okay, so it will not strike any other region. And that's the reason why it's called targeted therapy. It's a very promising technique of in nanomedicine that people are working on. Again, this is another example. So anyway, I'll stop here.